Today, we embark on a profound journey through the cosmos, guided by the unparalleled mind of Stephen Hawking. His seminal work, A Brief History of Time, isn't just a book, it's a narrative, a tale of the universe from the dawn of time to its potential ends. Over the next half hour, we'll explore the intricacies of space, time, and existence itself. So settle in and let your imagination take flight and join us as we dive into the mysteries of the cosmos. Chapter 1: Our Picture of the Universe. Our story begins in ancient times, a period shrouded in myth and wonder, where humanity first gazed up at the night sky and began to ponder its mysteries. Imagine a world where the Earth was the center of everything, surrounded by celestial spheres. This geocentric view, meticulously detailed by Aristotle and Ptolemy, depicted a universe where stars and planets moved in perfect, divine circles around our stationary planet. But the cosmos had secrets waiting to be unveiled. Fast forward to the Renaissance, and we meet Nicolaus Copernicus, a bold thinker who dared to place the sun at the center of the universe. This heliocentric model was revolutionary, challenging centuries of accepted wisdom. Picture Copernicus meticulously studying the movements of the celestial bodies, piecing together a model that shifted the very foundations of our understanding. As the story unfolds, we encounter Galileo Galilei peering through his newly invented telescope. Imagine his amazement as he observed the moons of Jupiter, craters on the moon, and the faces of Venus, observations that provided concrete evidence for the Copernican model. Galileo's discoveries ignited a scientific revolution, forever changing our picture of the universe. Johannes Kepler enters our narrative, refining the heliocentric model with his laws of planetary motion. Picture Kepler using the meticulous observations of Tycho Brahe to determine that planets moved in elliptical orbits and not perfect circles. This realization brought us closer to the true mechanics of our solar system, setting the stage for Isaac Newton's laws of motion and universal gravitation. Through this chapter, we witness the transformation of our understanding from an Earth-centered cosmos to a vast, dynamic universe. It's a tale of curiosity, courage, and the relentless pursuit of knowledge, a perfect prologue to our deeper exploration of space and time. Chapter 2: Space and Time. With our newfound perspective of the universe, we turn to the intertwined realms of space and time. Enter Albert Einstein, whose theories of relativity reshaped our very understanding of reality. Picture space and time not as separate entities but as a unified fabric, space-time, where the presence of mass and energy bends and warps this fabric. Imagine space-time as a giant elastic sheet. Place a heavy ball on this sheet and it creates a dip around it. This is analogous to how massive objects like stars and planets curve space-time, influencing the paths of everything around them. This curvature is what we perceive as gravity, a revolutionary idea that replaced Newton's notion of a force acting at a distance. Einstein's special theory of relativity, introduced in 1905, brought forth the famous equation E = mc², revealing that mass and energy are interchangeable. This theory also introduced the concept that the speed of light is a cosmic speed limit, constant and unchanging, regardless of the observer's motion. But Einstein wasn't done yet. In 1915, he presented the general theory of relativity, a more comprehensive framework that described gravity as the warping of space and time by mass and energy. Imagine light bending around massive objects, a phenomenon confirmed by the observations of starlight during a solar eclipse. This theory provided a new lens through which to view the universe, explaining everything from the orbit of Mercury to the expansion of the cosmos. As we navigate through this chapter, we begin to grasp the profound implications of relativity. Time is no longer an absolute constant, but varies depending on the observer's speed and gravitational field. This revelation challenges our everyday experiences and invites us to ponder the true nature of reality. Chapter 3: The Expanding Universe. The 20th century brought even more astonishing discoveries. Imagine Edwin Hubble working at the Mount Wilson Observatory, meticulously cataloging the distances and velocities of distant galaxies. Through his observations, Hubble made a groundbreaking discovery: that galaxies are moving away from us, and that the farther they are, the faster they recede. This phenomenon, now known as the Hubble's law, provided the first concrete evidence that the universe is expanding. Visualize the universe as a balloon being inflated, with galaxies as dots on its surface. As the balloon expands, the dots move further apart. This analogy helps us understand that the universe itself is growing, not just the objects within it moving through space. This expansion leads us to the Big Bang theory, suggesting that the universe began as an infinitely small, hot, and dense point around 13.8 billion years ago. Imagine a colossal explosion, not in space, but of space itself, marking the birth of the universe. This initial singularity expanded, cooled, and evolved, giving rise to the cosmos we observe today. The Big Bang theory also predicts the existence of cosmic microwave background radiation, the afterglow of the initial explosion. In 1965, Arno Penzias and Robert Wilson accidentally discovered this faint radiation, providing further confirmation of the Big Bang model. As we explore the expanding universe, we encounter dark matter and dark energy, mysterious components that comprise most of the cosmos, yet remain elusive to direct detection. Dark matter exerts a gravitational influence, holding galaxies together, while dark energy drives the accelerated expansion of the universe. These enigmatic forces add layers of complexity to our understanding, reminding us that the universe still holds many secrets. Chapter 4: The Uncertainty Principle. Leaving the vast scales of the cosmos, we shrink down to the quantum realm, where certainty becomes a luxury. Enter Werner Heisenberg and his uncertainty principle, which tells us that at the smallest scales, we cannot precisely measure both the position and momentum of a particle simultaneously. This principle introduces a fundamental limit to our knowledge, a core feature of quantum mechanics. Imagine trying to pinpoint the location of an electron. The more accurately we measure its position, the less certain we become about its momentum, and vice versa. This inherent uncertainty is not due to the measurement flaws, but is a fundamental aspect of nature itself. The uncertainty principle challenges classical physics, which assumes that particles have definite positions and velocities. In the quantum world, particles exist in a haze of probabilities described by wave functions. This duality of particles acting as both particles and waves is a cornerstone of quantum mechanics, leading to phenomena like superposition and entanglement. Superposition allows particles to exist in multiple states simultaneously until observed. Picture Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until the box is opened. This paradox illustrates the strange, counterintuitive nature of quantum mechanics. Entanglement, another quantum phenomenon, occurs when particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance between them. Albert Einstein famously referred to this as spooky action at a distance, highlighting the profound implications of quantum entanglement. As we delve deeper into the quantum realm, we encounter the probabilistic nature of reality, where certainty gives way to possibilities. This chapter invites us to question our classical intuitions and embrace the weightiness of the microscopic world. Chapter 5: Elementary Particles and the Forces of Nature. Within the quantum realm, we find the fundamental building blocks of the universe: elementary particles and the forces that govern their interactions. Imagine the universe as a grand symphony, with particles as the notes and forces as the melodies that bind them together. We begin with quarks and leptons, the basic constituents of matter. Quarks combine to form protons and neutrons, the components of atomic nuclei, while leptons include electrons, the familiar particles that orbit atomic nuclei. These particles interact through four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity, the force we experience daily, is the weakest yet most far-reaching, shaping the large-scale structure of the universe. Picture gravity as the curvature of space-time, guiding the motion of planets, stars, and galaxies. Electromagnetism governs the interactions between charged particles, giving rise to electricity, magnetism, and light. Imagine photons, the force carriers of electromagnetism, mediating these interactions at the speed of light. The weak nuclear force is responsible for processes like radioactive decay, transforming one type of particle into another. Picture this force at work in the heart of the Sun, enabling the fusion reactions that power our star. The strong nuclear force, the most powerful, binds quarks together with protons and neutrons and holds atomic nuclei together. Visualize this force as a mighty glue, keeping the fundamental particles tightly bound. As we explore these forces, we encounter the standard model of particle physics, a comprehensive framework that describes the interactions of all known elementary particles. This model has been remarkably successful, predicting the existence of particles like the Higgs boson, which has been confirmed by experiments at the LHC in 2012. However, the standard model is incomplete. It doesn't account for gravity's quantum aspects, and it leaves questions about dark matter and dark energy unanswered. Physicists continue to search for a more unified theory, a quest that drives our story forward. Chapter 6: Black holes. Our journey now takes us to the age of the known universe, to the enigmatic realms of black holes. These cosmic giants are the remnants of massive stars, collapsed under their own gravity to form singularities, points of infinite density where the known laws of physics break down. Imagine a star several times the mass of our Sun, reaching the end of its life. As it exhausts its nuclear fuel, it undergoes a supernova explosion, shading its outer layers. The core, unable to support itself, collapses into a black hole. The resulting gravitational field is so intense that not even light can escape, creating an event horizon, which is the boundary beyond which nothing can return. Picture the event horizon as a one-way membrane. Anything crossing it is lost forever to the outside world. This boundary defines the black hole, marking the point of no return. Black holes come in various sizes, from stellar mass black holes formed by collapsing stars to supermassive black holes lurking at the centers of galaxies, with masses millions to billion times that of the Sun. These titanic black holes power quasars, some of the brightest objects in the universe, by accreting matter and releasing immense energy. As we venture closer to a black hole, time itself seems to slow down, a phenomenon predicted by general relativity. Imagine an astronaut approaching a black hole. To a distant observer, their descent would appear to slow and eventually freeze at the event horizon, while the astronaut would experience time normally, witnessing the universe's future in fast forward. Black holes are not just destructive. They play a crucial role in the evolution of galaxies, influencing star formation and the distribution of matter. Their gravitational waves, ripples in space-time, were detected for the first time in 2015, opening a new window to observe the universe. In this chapter, we explore the mysteries and wonders of black holes, these cosmic enigmas that challenge our understanding of physics and push the boundaries of our imagination. Chapter 7. Black Holes Ain't So Black. As we delve deeper into the enigma of black holes, we encounter one of Stephen Hawking's most groundbreaking ideas. Black holes might not be entirely black. Imagine black holes not as eternal prisons for matter and energy, but as objects that can slowly evaporate, releasing particles over time. This revolutionary concept comes from Hawking's work on quantum mechanics and general relativity. In the early 1970s, he proposed that black holes could emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, suggests that black holes can lose mass and energy, eventually leading to their evaporation. Picture a black hole slowly radiating away, its mass dwindling over billions of years. This radiation arises from particle-antiparticle pairs that spontaneously form near the event's horizon. One particle falls into the black hole, while the other escapes, effectively reducing the black hole's mass. This process challenges our understanding of the permanence of black holes and introduces profound questions about the fate of information swallowed by these cosmic giants. Hawking's theory has significant implications for the study of quantum gravity and the unification of physics. It suggests that information might not be lost forever in black holes, as previously thought, but could be preserved in some form, leading to the famous information paradox. This paradox remains a hot topic in theoretical physics, pushing scientists to seek deeper insights into the nature of black holes and the fundamental laws of the universe. In this chapter, we witness the evolution of black holes from mysterious cosmic traps to dynamic entities that interact with the quantum world. Hawking's insights illuminate the path towards a more complete understanding of the cosmos, blending the macroscopic and microscopic realms. Chapter 8. The Origin and Fate of the Universe. Turning our gaze to the grander scales, we ponder the ultimate questions. How did the universe begin? How will it end? Imagine the universe as a vast, ever-changing entity with a history that spans billions of years and a future that stretches into the unknown. The Big Bang Theory provides our starting point, suggesting that the universe began as a singular, infinitely dense point around 13.8 billion years ago. From this initial explosion, space and time expanded, giving rise to the cosmos as we know it. Picture the early universe, a hot, dense soup of particles and radiation, gradually cooling and coalescing into atoms, stars, and galaxies. As the universe expands, it evolves through different eras, from the formation of the first stars and galaxies to the development of complex structures like galaxy clusters and superclusters. This dynamic evolution is driven by fundamental forces and governed by physical laws that remain consistent throughout space and time. But what does the future hold for the universe? Several scenarios are possible, depending on the nature of dark energy and the total mass of the universe. One of the possibilities is continued expansion, where the universe grows colder and more diffuse, leading to a big freeze where stars burn out and galaxies drift apart. Another scenario is the Big Crunch, where gravitational forces could eventually reverse the expansion, causing the universe to collapse back into a singular state. Recent observations suggest that the expansion of the universe is accelerating, driven by dark energy, a mysterious force that permeates space. This acceleration points towards a third scenario, the Big Rip, where the fabric of space-time itself could be torn apart, disintegrating galaxies, stars, and even atoms. Hawking's work explores these possibilities, weaving a narrative that spans from the Big Bang to the potential end of the universe. It's a story that invites us to reflect on our place in the cosmos and the transient nature of existence. Chapter 9. The Arrow of Time. Time, it seems, marches ever forward, an unyielding flow from past to future. But why does time have a direction? Hawking delves into this profound question, exploring the concept of the arrow of time and its connection to the second law of thermodynamics. Imagine time as a river, flowing steadily in one direction. This unidirectional flow is tied to the concept of entropy, a measure of disorder in a system. The second law of thermodynamics states that the entropy of a system always increases in a closed system, leading to the inevitable progression from order to disorder. Picture a cup of hot coffee cooling down to room temperature. The heat energy disperses, increasing the overall entropy of the system. This process is irreversible, aligning with our everyday experience that certain events can only happen in one direction. We never see a cooled cup of coffee spontaneously heat up, just as we don't see broken cups reassemble themselves. This increase in entropy defines the arrow of time, giving it a direction and distinguishing the past from the future. But why did the universe begin in a state of low entropy? Hawking explores this question, suggesting that the Big Bang set the initial conditions for a universe with a well-defined arrow of time. In our daily lives, we experience the arrow of time through memory, causality, and the unfolding of events. This chapter invites us to ponder the nature of time itself, challenging us to think beyond our conventional understanding and explore the deeper principles that govern the cosmos. Chapter 10. Wormholes and Time Travel. What if we could bend the arrow of time? Enter the realm of wormholes, hypothetical tunnels through space-time that could connect distant parts of the universe. Imagine stepping through one end of a wormhole and emerging light years away or even in a different time. Wormholes are solutions to Einstein's field equations, theoretical constructs that arise from general relativity. Picture space-time as a two-dimensional sheet. If you fold this sheet, two distant points can come into contact, creating a shortcut. This is the essence of a wormhole, a bridge between distant regions of space-time. The possibility of wormholes raises fascinating questions about time travel. If we could traverse a wormhole, could we travel to the past or the future? This idea, while speculative, has captivated scientists and the public alike, inspiring countless stories in science fiction. However, the practical realization of wormholes faces significant challenges. They require exotic matter with negative energy density to remain stable, a type of matter that has not been observed. Even if such matter exists, traversable wormholes might pose paradoxes, such as the famous grandfather paradox, where a time traveler could potentially alter the past and affect their own existence. Despite these challenges, the study of wormholes and time travel pushes the boundaries of our understanding, inviting us to explore the limits of physical laws and the nature of reality. Hawking himself considered these possibilities, blending rigorous science with imaginative speculation. Chapter 11. The Unification of Physics. Our journey nears its end with the quest for a unified theory, a theory of everything that can seamlessly explain all physical phenomena. Picture scientists striving to merge general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the microscopic world. This quest for unification has driven some of the most significant advances in physics. String theory, for example, proposes that all particles are tiny vibrating strings, each with its own frequency. These strings exist in a multi-dimensional space, with additional dimensions beyond the familiar three of space and one of time. Imagine a universe where particles are not point-like but extended objects, vibrating in a higher dimensional space. String theory aims to reconcile general relativity and quantum mechanics, providing a single framework that encompasses all forces and particles. However, string theory is not without its challenges. It requires complex mathematics and predicts a landscape of possible universes, making it difficult to test experimentally. Despite these hurdles, the pursuit of a unified theory remains a central goal in theoretical physics, driven by the desire to understand the underlying principles that govern the cosmos. As we explore this chapter, we recognize that the quest for unification is not just a scientific endeavor, but a philosophical one. It seeks to answer profound questions about the nature of reality, the origin of the universe, and our place within it. And so, we conclude our odyssey through Stephen Hawking's A Brief History of Time. We've traveled from the ancient skies to the quantum realm, from black holes to the birth and death of the universe. As we sign off, remember that the universe is vast and full of wonders, and our journey of discovery is far from over. Hawking's legacy lives on, encouraging us to keep exploring, keep questioning, and never lose our sense of wonder.